Hello and welcome to Object-Oriented Programming. Today is all about smart pointers, and in the beginning we talk a bit about casts. We are in lecture 6 already, so only 2 more remaining. Next time, we have a break after today's lecture for about a month. So there's the Easter break and then there's the 1st of May. So in 4 weeks' time, the next lecture is, but I think so what we talk about today, we have all the basics, what you also need for the assignment 2. Maybe operator overloading is also interesting, but I think smart pointer is a bit more important for the assignments. That's why we moved it to this 6th lecture for today. So smart pointers are very cool feature. You will see it today and you will love it for your assignments. Trust me. Okay, so as always in the beginning, let's do a short recap. Michi and Julia discussed exceptions and we have again a quiz for you. And let's see if you understood what they showed you a few minutes ago. So we have my base class or my base exception here, which is derived from the STD exception on top. Then we do once more and derive from my base exception and create our my derived exception, create our own constructor here. And then we have a function, my function, which throws this my derived exception. And the question now is, what is the output? Okay, last few seconds for you to decide. It wouldn't be a recap if there is not one pitfall in it.
As always.
As always, yes. Okay, so let's see what you voted for. Oh yeah, great. So Michi, Julia, you did a great job. This looks good. Okay, so why is it B? Let's have a closer look why. So we throw this my derived exception here. My derived exception is also from type my base exception and is also from type STD exception. So this is thrown here. And the first catch block is a my base exception. And as we now know, the first fit of the catch block is taken. So in this case, my derived exception is a my base exception because it's derived from that class. And the B is printed and this catch block and this catch block is not reached because the first one that fits is taken. Any questions to this? I think it's, yeah. Yeah?
So catching the exception takes precedence before finishing the creation of the exception object.
Catching the exception?
Because when we call my derived exception, we first have to create a base exception object, and it just catches it before the actual creation of my derived exception stage.
So you mean with this line here, we are creating a myBaseException object?
No, I mean when we throw the myDerived exception.
Yeah.
We are creating myDerived exception object, but since it's derived from the base
Yeah.
exception, it first creates the base exception, and the catch just doesn't wait for it to finish creating the object. It just catches the first one that it gets, in this case, the base exception.
So when I write it like this and create an object myDerived exception, as we know, first the base class is created, then the subclass is created, and so on. So first the STD exception is created, then the myBaseException is created, then the myDerived class is created. The object is created fully. So the object is as a whole created and then thrown as one object of type myDerived exception. And then this object, myDerived exception, is also from type myBaseException. And that's why it's called here. Okay, then let's continue. That was already the recap. Let's talk about casts. I think Michi and Julia also showed it last time, the dynamic cast. Yeah, we will also talk about that. But first, a short motivation. You of course know the C-casts. C-casts has this notation where you write the new type in the parentheses before the expression. So for example, if you have here a float and you want to cast it to an integer, you write it like this. In C++, it's a bit more to write. You have 4 different types of casts. The dynamic cast you already discussed in the practicals, but we'll also have a look at it now. Static cast, const cast, and reinterpret casts. Each of them has its own use case, and it is kind of the same as the C casts, but they are a bit more safer to use. But let's have a look at it step by step and cast by cast. So the static cast is maybe the most commonly used cast, and it's pretty similar to the one you have used in C. This is a compile time conversion. So at compile time, the conversion is checked, and if it's not possible, it's a compiler error. That's pretty cool because we now know at the compile time that there is an error and not only at runtime. So for example, I have here an integer and I want to cast it to a double. That works. So I always write static cast and then the new data type and here the variable I want to cast. Or I have an integer and I want to have the address of this integer, cast this to a void pointer, and I can also then cast this void pointer, for example, to an integer pointer. Of course, I could also use other pointers here. This is just an example. I could also write here the address of I is an integer pointer, then I would not need a static cast for that. But in this case, it's safer to use the static cast because the compiler checks if this is correct or a correct conversion.
I may have a question at this point. Is it also possible to cast from a base class to a derived class? So for example, from an animal to a lion, for example?
Not with the static cast. There is another cast which can do this, and this is the dynamic cast. Dynamic cast performs a so-called downcasting from the base class to the derived class. And this is again a bit of an advantage of the dynamic cast. This works now at runtime. So when you use your C cast, it is kind of checked, but not really. You can get into big troubles if the conversion does not work. Maybe it is converted to your other data type, but it's not valid. So you don't know what happens, maybe a segmentation fault. But with the dynamic cast, it's very cool because if it's not possible to convert, let's say from a lion to an animal, from the animal to the lion, then it returns a null pointer. or it throws a bad cast exception. So you can always then work with that return value or catch the exception. So at runtime, again, you don't have the problem of have a segmentation fault of your program if your conversion does not work. You can ask if there is a null pointer, or you can catch the bad cast exception. For the dynamic cast, there's just one thing you have to implement. There should be, or there have to be at least one virtual method in the base class so that it works. Let's have a look at a short example. We have our animal class again. We have our lion class here. They have one common method, the eat method. And when I call or create a new lion, and I store it in an animal pointer, then I can at some point convert my animal pointer to a lion again. So I know that this is a lion, so I can perform this dynamic cast to a lion pointer. And this is then a downcast from the base class, from the animal to the lion. And if this does not work for any reason, maybe it's not a lion because I have also other animals. If it's not a lion, then in many cases I would get using the C-cast a segmentation fault, but with this I only get a null pointer and I can check if this is a null pointer here. It obviously failed, or if it works, then I can use this pointer. So this is a kind of an additional feature from dynamic casts. It's more type safe and you can react on the return value or on the bad alloc exception, not the bad alloc, bad cast exception if there was an error. Okay, the third cast is the so-called const cast. This is one you should maybe avoid if possible. It removes the constancy of variables. So you will face the situation where you have an object that is const, but then you will maybe modify that. So in this case, we have our getLion function, which returns a const lion pointer. So it creates a lion, returns that lion pointer, and when I do it like this, so this here, this getLion returns a const lion pointer, but I store it into a normal lion pointer, I will get this error. This means you have a const lion pointer. You cannot store it into a lion pointer. This also has to be a const lion pointer. So this left one here has to be const as well, because otherwise we would be able to change this lion. This should not be able, should not be possible. With the const cast, you could do that. So you can write const cast lion pointer and get the return value of this getLion. And this basically means, okay, I know that this is a const lion, which I get returned from this getLion, but I now want to remove this const and make it a normal lion, which I can modify. There are not many possibilities for you, to be honest, where you should use it. In most cases, if you want to use a const cast, you have some kind of problem in your structure, in your class structure, because in most of the cases, let's say the getters should be const. And if you have a getter and you want to return the object, maybe it should not possible to modify that object. So if you want to use the const cast, maybe consider to recreate your methods, write new methods that do what you want to do, and not use const cast. So if possible, please avoid them.
Do you have an example where I would need such a const cast in practice?
I think I don't know when I ever used, or if I ever used it. Did you use it?
I'm not sure, but maybe just to, modify an object that I have just for debugging purposes, just to make short changes and output them. But these are
but maybe during development.
Yeah.
So when I'm currently developing, and then I have one object. Okay, let me just have a look and try this out. Then I can use a const cast, but not for the final submission. Then, yeah. The last one is the so-called reinterpret cast. And this converts, this is basically the, do whatever you want. Because this converts any type to any other type. Without checks, so there are no exceptions. It's just do whatever you want. And again, avoid this if possible, because if you have to do a reinterpret cast, you maybe have a problem in your class structure again. So what you could do, for example, you can create a lion and you can cast this lion pointer to an int pointer. Does not really make sense because you lose a lot of information, but this would work. You could also cast this lion pointer to a long. It will work because, this is just a pointer, and integer is also just a pointer, and long is also just a pointer. Oh, long is not a pointer, but long is an address, 8 byte, and the lion pointer is also 8 bytes, so it will work, but there's no real need to do that. So reinterpret cast, again, I don't know if I ever used it, but
and this is also not the thing that we want to use when we, for example, want to convert strings to integers, right?
Yeah. So this is also not really the best way for some conversions. For example, if we have a string and want to convert it to an integer. Yeah. Okay. One quiz for you. We talked about the dynamic cast because this is maybe the most important one. Which scenario do you think is the most appropriate for using dynamic casts? Okay, let's have a look what you decided.
Great.
Yeah, that's great. So the best case or the perfect scenario for the dynamic cast is you convert a base class pointer to a derived class pointer with runtime type checking. This is the benefit of it. Converting a derived class pointer to a base class pointer, is also possible. But for that, you could also use a usual cast or no cast, because we also used it many times. You have a base class object, you have a derived class object, and store it in a pointer from the base class. Okay. Now the question might come into your mind, why should I use C++ casts over C cast? Because there is a lot more to write. And we are quite lazy sometimes. There are a few benefits. So C++ casts are checked by the compiler or also at runtime sometimes if you use the dynamic casts. So it fails at compile time or throws an exception. The casts are depending on the use case. So whatever type of conversion you want to do, you have a better you can split it up into different types of casts. And it's easier to find in code because you can just look for dynamic casts, Control F dynamic cast, and then you know where in your project you're casting. That's not so easy if you use C casts. Then it's harder to find where you cast. And they are not checked in C casts. They fail at runtime. Then you have most likely a segmentation fault. And there's just one cast for all the use cases. My personal opinion, to be honest, if you know what you're doing, you can use C casts. But if not, you might have bigger problems. So in the practicals, I would recommend using C++ casts to get used to it and to be safe, because otherwise it's a harder time to debug your problems. Okay, any questions to casts? So there's 4 types of casts. If not, then we will come to a second topic today, which, I think it was already discussed also in the practicals. They did a lot of us for us already.
Correct. It's the concept of shallow copy versus deep copy, and as David already mentioned, you've heard about it, I think, in the second part of the practicals. So it's more or less a repetition now, but as you know, the lecture and the practicals are independent courses, and so we want to cover this topic here in the lecture part as
and
well.
It's very, very important.
Yes.
Because it's a usual pitfall for beginners. That's why it's a good idea to, at least you have heard it. So let's talk about it again.
Yeah, and why it's so important. Let's have a look into one example that we've prepared. So we have here a pet class with 2 members, which is a string and an age. It's an integer pointer. Doesn't make that much sense, but you can also imagine another class where you have a pointer where you then will have heap memory that you will have to allocate. Then we have a constructor where we just assign values to our members, the name, and we allocate heap memory here for our age integer pointer. Then we have here a copy constructor, which is basically the default copy constructor, just copying all our members, the name and the age. And then we have a print method where we print the name and the age of our pet. And we have also a setup for the age. In our main program, we then create an object which is called Rex and has the age 5. And then we, call the copy constructor by, having another pet, which is called dog copy in this case. And this should get the same values as our previous object, right? So Rex and 5. If I then print our dog, it should print our dog, and then the dog copy should print the dog copy values. Then what we do here is we call the setter for the age for our first object, the dog object, and set it to 6, meaning that we change the age of our dog. Afterwards, we print the dog and the dog copy again. And what do you think is the output now of this program? Yes? Okay. So first it would be 5, and then it would be 6 for both objects. That's correct. So we have Rex 5, Rex 5. This is the print for the dog and the dog copy. And after setting the age for the dog, we get Rex 6 for sure, but also for the dog copy, we get also 6, which is something we wouldn't expect, or this is not something that we want to have as a behavior of this program. So let's have a look why this is the case. So we have our first object here, which is here on the stack, with the name, which is the string, and, as we remember, an integer pointer, pointing to memory that we've allocated on the heap with the value 5. If we then copy this object with our default copy constructor, all our members get copied. So we copy this string here, and we also copy this pointer here, meaning that we have for our dog copy the same string which got copied and also the pointer that got copied, but we have for sure here now the same pointer address pointing to the same memory on the heap. If we now call the setH method of the first object, we change this value here, and if we then look what has the dog copy, which h has the dog copy, it has for sure the same as the first one, so we work on just one similar integer in this case. And this is called a shallow copy, and this is something we do not want in most cases. So do you have any ideas of how we can get rid of this problem? What do I have to change in our code that we have a real copy then of the dog, so that we have two independent objects? Yep.
So we'll just in the copy constructor make a new pointer and just copy the value from the given one into it.
Yeah, thank you. That's correct. So in this case, we just have to change the copy constructor where we first have just copied our pointer, and we have to change it to allocating new memory on the heap as well and storing the new pointer in this h value. So we then have a separate space of memory for a separate second h integer value on the heap. So let's have a look. After changing it, we then have rex5 here at the end, which is what we want to have. Looking to our memory again, in this case we now allocate new memory for this pointer here, meaning that we have a separate h value on the heap. And if we now call the set h method of the first dog, then it just changes this value here, and this is for sure a different one than the second dog has. And this is the deep copy which we want to have in most cases in practice.
Yeah. So with this, so it's just an integer pointer, and this is maybe a bit obvious, but in many cases you will have classes as members of other classes. So for example, if you have a player class and the player maybe has weapons, then it has a vector of different weapons. And if you want to copy the player, maybe also the weapons should be copied. So the whole vector should be copied, and they shouldn't use the same weapons. So, or if I have a phone and I create a copy of it, my copy shouldn't use the same phone. So maybe the copy gets another phone. And this is very important that you use this deep copy mechanism if you use the copy constructor, because it's, again, very, very hard to debug. It's not that obvious to find. You maybe have to draw it, as you have done it here, to find these problems. So, if you use the copy constructor, always have a closer look if you use dynamic memory at some point, and then think of how you can copy this dynamic memory.
Mm-hmm. To sum it up, just to highlight the both differences here again, the shallow copy copies just the data of your object without really copying the data from the heap. So heap is here the keyword, I think. Whenever you use the heap, make sure that you manually, so to speak, copy also the values on the heap. Yeah, and the deep copy is what we want to have. This is the mechanism to have real copies from not only the stack, but also the heap memory values.
Okay, any questions to deep copy, shallow copy?
Okay.
Great. If not, then let's come to our main part of today, smart pointers. And they are actually very smart, and it's a very, very cool feature. Before, let's start with a bit of a motivation. What do we not like about pointers? In general, if we have something like this, we can create memory leaks. So we have our superhero. We know this class already. It has a constructor, just printing created, so the name and created. It has an attack method that prints the name and attacks, and a destructor name and destroys. And then we create this superhero here as a normal heap object with new, so we get a pointer back. And if we use it like this, the destructor is never called, because I do not call here delete hero. So my output is just Batman created, and I will have memory leaks if I use it like this. So memory leaks is annoying when you use the heap and usual pointers. The second thing that can make troubles, let's go one step further. Okay, let's delete our hero, but maybe afterwards in my program I still want to use it, or I've forgotten that I deleted my hero here and I want to call attack. So this is a so-called dangling pointer. So we're using a pointer after it was already freed, and this results in a segmentation fault. This is also, not very cool to have this segmentation fault, because it's hard to identify where this happens or where this comes from. So pointers can use memory leaks or can cause memory leaks, create these wild and dangling pointers, and have to be freed or deleted whenever they are on the heap. In short, I often was like him. So smart pointers are a great solution for that. They are own classes wrapped around these normal pointers. So they act like you have the real pointer. So they can also throw bad alloc exceptions, for example, if you use the heap. But they destroy themselves on their own. So you don't have to think about, okay, when do I have to delete this pointer or this memory location on the heap? So with smart pointers, you will not have any problems with Valgrind anymore, because it gets deleted for you. And this is a huge advantage, I think. There are 3 types of smart pointers, and we will go through all of them now. So there are the unique pointer, the shared pointer, and the weak pointer. You have to include this memory header, and then you can work with it. I know it is, again, a bit hard to write, but we now know C++, it's always not that easy and a bit more to write. But I think, especially for smart pointers, it's very, very useful. So yeah, let's try it. We say we have 3 types of pointer: the unique pointer, the shared pointer, and the weak pointer. Let's start with the easiest one. It's the unique pointer. The unique pointer is an object, and it points exactly to one other object. So you have here this unique pointer, and what you cannot do is you cannot copy this unique pointer. This unique pointer here is just one object, it's an own class, and it has as a member one pointer to my superhero object, which is maybe on the heap. But I cannot copy it. So I only have one reference, one pointer to my superhero object. This is also called exclusive ownership. So there's only one pointer to my object. If I want to copy it, it will not work. Let's have a look how it is implemented in the code. So let's create again our superhero. We know that we have our constructor, the attack method, and the destructor. And how we create this unique pointer is now a bit, much to write. You have to call std make unique and hand over the superhero in this case, so the data type of the class you want to create. And then you call here the constructor with this, and it returns a unique pointer. Again, std, unique pointer, superhero, and then the variable name, in this case S1. And when we remember, we go back to this example here, we created a new superhero and we had memory leaks because it was not destroyed. So the destructor was never called. When we go back to the unique pointer, we will not have memory leaks. All heap blocks are freed, memory, the Batman is created and the Batman is destroyed here. So as soon as this variable here, S1, is out of scope, which means as soon as the main function is over, it gets deleted on their own. So we don't have to think about again, do we have to free this? Do we have to delete this? No, we don't have to do this. And it's also stored on the heap. So this Batman here is stored on the heap. So the unique pointer and also all the other smart pointers always gives you memory or allocates memory on the heap. So this is a very, very cool feature here. As I said before, let's go back to this raw pointer. At the raw pointer, we had this memory leaks, but this does not work for the unique pointer, or it's not necessary to delete it. What happens if I want to copy this unique pointer? So as we have seen before, we are not allowed to do it. Let's try out and create our superhero std unique pointer. And with this call here, the copy constructor is called, I will get an error. It's not possible. If I do it like this is also another way to create a unique pointer. I will get an error. This is also not possible. And also, if I call my function, call attack, this is not possible to call. So S1, which I created here, is not possible because, as we know, this will create a copy. So the copy constructor is called. This will create a copy of my superhero here, and copying is not allowed, so it will also create an error here. When you use smart pointers, so for example like this, you can use it like the usual pointers using this arrow operator here. So you also know it from C. If this hero would be a pointer, you can write hero attack with the arrow, and it's the same when you use smart pointers. So this is similar. Do you have any idea how they achieved that all of this is not possible? So I cannot create a copy of it. Yes. They delete the copy constructor. Yes. So in this std unique pointer class, the copy constructor and also the assignment operator, but we will talk about that next time, is deleted. So yeah, it's not possible to create a copy. There are two solutions to kind of use unique pointers and kind of copy that. You can use the .get method. And what this does is, it does not copy this unique pointer object. It only gives you the pointer, so the raw pointer to the object. So what you can do is s1.get, store that in a superhero pointer. This is like a C pointer, or we also know it from C++ now. And this then will be a normal superhero pointer, and this, of course, can be copied. You can also write it like this. So call the method with the unique pointer, but then here you have to specify the argument as superhero pointer, not as a unique pointer. But be careful with that, because as soon as the unique pointer is out of scope, it gets automatically deleted. So you have to pay attention, how long is my pointer valid? And when I create this S1 here, it will get out of scope when I'm here. Okay, I can live with that because the main then is over. But when I have a construct like this, Kate, a bit artificial, but let's have a look at it. I create a smart pointer, so a unique pointer inside this if. So this if is here over. So the scope of S1 ends here. And I cannot use it below because my object is already destroyed. So not only my smart pointer to the superhero is destroyed, but also the superhero itself is destroyed. So I cannot create it and let it go out of scope and then use it for whatever I want to do. This will also result in a segmentation fault.
So if I use this get method, I some kind of break out of this concept of smart pointers, and then there is the possibility again of have some dangling pointers.
Yeah, exactly. Yeah. So use get also very wisely, and I think many of you now ask, why should I use the unique pointer? Wouldn't it be better to have many copies of the same pointer? This is the next pointer we want to show you, but the unique pointer is the most basic one, where we only have one object, one pointer to one object, and not more than one. The second solution using unique pointer would be to call the move, std move, which then takes the ownership of one smart pointer, of one unique pointer, and gives it to another one. This looks like something like this. So I have my unique pointer here. This has a pointer inside as member to my superhero and my superhero object. And when I call this move, it creates a second pointer, again with the same pointer, but it also sets the other unique pointer, so the first one, to null. So this one is invalid and this is valid. So I still have only one unique pointer pointing to the object.
So this is not really a copy, a duplicate, so it's really a move.
Yeah, it moves from one object to the other. For example, if we go back, you know here that you will not use your S1 anymore in this function, but you want to use it in this call attack. You can move it there. Any ideas how they implemented that it's automatically deleted? So the object is automatically deleted on the heap. So I don't have to call free anymore. So when it gets out of scope here, yes?
They just implemented free in the destructor of the object?
Yeah, they just implemented delete in this case in the destructor of the unique pointer. So it has this superhero pointer, it points to this location, and whenever this unique pointer object is out of scope, which means it gets destroyed, the destructor of this unique pointer here is called. And if the destructor of this unique pointer here is called, there is just maybe one statement inside, delete the superhero object 2. So I don't have to, take care about that. And basically I don't have to delete it anymore. That's very cool because it gets deleted automatically. Okay, one question for you. Let's see how this works now. We have, again, our similar superhero class, and we have a function, create superhero, that returns a superhero pointer, and it creates inside a unique pointer and returns then the unique pointer.get, so the pointer to it. The question is now, what is the output? So the questions here are now, when or is the constructor, the destructor called? When is the attack method called? Is it called?
Does it compile?
Does it compile?
Is there a runtime error?
Okay, a few more seconds. Okay, it's a runtime error. Yes. Let's have a look at it, what happens here. So we create our unique pointer. This std make unique superhero Batman will call the constructor because it creates the object on the heap and also creates the smart pointer, so the unique pointer, which then points to the object, to the superhero. So this works perfectly fine. We store then this in a variable s1, and we return the pointer. So basically the pointer to the object. But s1 ends here, so as soon as this create superhero function is over, also the s1 scope ends, which means it actually deletes our superhero. So we have here now a pointer to a destroyed object because the object is already destroyed. That's unlucky. We don't want that. And there is luckily a solution, and this is shared pointers. And shared pointers are maybe the most used type of smart pointers because they allow you to have more than one smart pointer pointing to the same object. And only as soon as all of them are out of scope, the object is destroyed. That's very cool. So we can now create a shared pointer, and this can have arbitrary copies of it. The object itself only exists once, but I can have more than one pointer, smart pointer, shared pointer pointing to the same object. And the object gets destroyed automatically as soon as all of the shared pointers pointing to the superhero are out of scope, which means they are also destroyed. Okay, let's have a look again. It's the same as before. In the unique pointer, we have our superhero, and we call make shared instead of make unique. Again, what type? We want to create a superhero, call a constructor. So this line here again calls the constructor of our superhero and also creates the shared pointer, which points to my object, my superhero. I store it into a shared pointer, and then I call attack. And now, without deleting it, Batman created, so the constructor, Batman attacks, so this one is called, and Batman destroyed. So this is basically the behavior I want to have. I don't want to write delete here anymore, and I can use it like this. But now we can also copy that. So that's the difference to the unique pointer. Again, we create our shared pointer here. We can now also use something like this. So assign this, which again, the copy constructor is called. We can use it like this. Also, the copy constructor is called. And we can also use it like this for function calls. And here also the copy constructor is called. So the copy constructor is obviously not deleted for the shared pointers, which means it works that I can create many copies of my pointers. And yeah, the output is the same. Again, what's very, very important, what I struggled most in the beginning, so I stressed this, I think on nearly every slide. When I have like this, only the smart pointer is copied. Yeah, so the copy constructor of the smart pointer is copied, not the object, so not my superhero. We talked about deep copy and shallow copy before. This is actually a shallow copy.
That we want to have in this case?
In this case, we want to have the shallow copy because we don't want to have a copy of my superhero. I just want to have a copy of my shared pointer, which points to the same superhero.
So in this example, we would have 4 shared pointers, right? And only one pointer to our superhero, which is stored in all those 4 pointers.
Yeah, exactly. So we call here once the copy constructor, twice, and a third time. But as you can see, the output is only once for the superhero because it gets created here. I copy my shared pointer using the copy constructor, but not the object itself. If the object would be recreated and copied, I would have the output here more than once, because then I would have a copy also for my superhero. But as you can see, only the shared pointer is copied. They're using the same object. And now I can also use it like this. We also had that before. We have our function create superhero, which created now a shared pointer. I can return this shared pointer. This will create a copy of my shared pointer and pointing to the same object. And this will now work. I can take this because there is always at least one shared pointer pointing to my object. So my object will not get destroyed here because I return a copy and my superhero is still alive, and it is alive as long as at least one pointer, one smart pointer points to this object.
So to sum it up, those shared pointers are basically similar to the unique pointers without the exclusive ownership and with the ability to be copied.
Yeah,
But how does it work?
There is a so-called control block behind this shared pointer. And this control block stores some additional information. I don't want to get too much into detail. There is a detailed Stack Overflow description linked for you if you want to have a closer look at it, how it is implemented. But basically what is implemented is a so-called reference counter. And this reference counter is just a number that counts how many pointers currently exist to that object. All of my shared pointers do have this reference counter, and as soon as this reference counter is set to 0, because I have no more shared pointers, the object gets destroyed from the last shared pointer that uses this. So basically, in the destructor of my shared pointer is kind of an if statement. If I'm the last one pointing to this object and I'm getting destroyed now, then also please destroy the object. That's basically it. And there is a function or a method of shared pointers. It's called useCount. And this will return you the current number of pointers to this object. The current number of shared pointers, not raw pointers. That's important.
Then I can call it on average of the copies.
Yeah,
on
you
every
can call
copy.
it on everyone, and all of them have the same number of pointers. So use count should be always the same for all of the shared pointers. Okay, let's have a look at this example. This is the ref counter, and I want to have a look now how many pointers are pointing to my object. I create here my shared pointer, S1. And then I use S1 useCount. What do you think is the output of this line here only? Sorry? Yeah? 0. Why 0?
Because I'm guessing it's same as the index that starts from 0. Because there are technically no copies. This is the first one, so there are no
Yeah, but this is the absolute number always. So use count gives you the absolute number of shared pointer pointing to the object. It's not starting with 0, it's really the absolute number. So would assume it's 1, but it's 0.
But why is that?
Why is it 0? We are not creating the object with this line. We just declare a variable, a shared pointer variable S1, but we do not create with this make shared. So we're not creating the object. We just declare, like I create int x, and don't give it a value. It's just there, but it has no value. So this one is 0. Okay, now I want to initialize my variable with make shared. I create my superhero object and I write it into this S1. What will be the output now from this use count? 1. Yeah. So you can see also here the constructor is called now S1 S1 use count is 1. Now I call the copy constructor, so I create another shared pointer. As you can see, the constructor from Batman is not called because I only create a copy of my shared object, not from the object itself. What is now the output here? I call S1 use count, so for my first, and S2 use count. 2, yeah. So both have the value 2 inside, so both know that there is a second one pointing to this object. So if one of them, let's say S1, gets destroyed because it's out of scope, it will not call the destructor of the superheroes. It will not destroy the superhero object because it just says, okay, I'm not the only one. I will reduce now the ref counter by 1, but I will not destroy the superhero object. So the last one living will destroy it then. Yes?
One very stupid and applicable question, but if we were to destroy the object that the shift pointers are pointing to before they go out of scope, so they still exist, but they are, let's say, null pointers. And if we then call use count, will it display 0 no matter how many copies exist?
So you mean if you destroy the superhero object?
But not the
And not the smart pointer. Yeah, then of course you will get into trouble because you cannot use the smart pointer anymore because the object is already deleted. The use count will not be decremented because the use count would only be decremented if you destroy the smart pointer. Yeah. So you can most likely have the use count 2. But you don't have the superhero object anymore. Yeah, so I would not do this. I would not mix it. I would, if you decide to use shared pointers, stick to them, and they will do the magic for you. So you don't have to delete things anymore. As soon as they are out of scope, it will be deleted.
Maybe a follow-up question to this. So obviously there is some overhead in using such smart pointers, right? So they have this reference counter and some logic behind that. Should we use it in practice always, or should we sometimes stick to our raw pointers?
So in our course, I think it's a good idea to use it because we don't take too much consideration of overhead. It's basically 1 or 2 small additional integers that count. We can deal with that in OOP1 at least. So smart pointers, I think, or at least especially shared pointers, are a good idea, especially for assignment 2 to use, because yeah, it will save you a lot of time when creating objects on the heap. But there is, and then of course the object gets destroyed when it's out of scope. There is one more pointer. It's so-called the weak pointer. And this is, again, I don't know if I've ever used it, to be honest. It's again, you kind of trick the shared pointer a bit. It is similar to a shared pointer, pretty similar to a shared pointer, but it does not increment the reference counter. So you can create kind of a copy of a shared pointer and store it in a weak pointer, but this will not increment the ref counter, which means you have kind of you're not always sure if this still exists, and you're most likely should use it with caution because, it might not exist anymore.
This reminds me somehow to the case with the unique pointer where we use the get method. Yeah, where we do not have the control, the full control. What happens with the pointers? Yeah,
exactly. So you have also the same pointer, but the ref counter is not incremented. Sometimes it makes sense for like observing an object and see if this still exists. Or it's already destroyed. But in most of the cases, to be honest, you would use the shared pointers. But let's have a look at the weak pointers. You create them the same as the shared pointers. So make shared. There is no make weak because you always should use it in combination with the shared pointers. And what you can do now is you can create a copy of it, and in this case, store the copy in a weak pointer. What do you think is now the output of this S1 use count?
1.
Yeah, it's 1. So again, our constructor is called, then it's 1. We have 2 pointers, but one of them is a weak pointer. Weak pointer does not increment the ref count. So as soon as this pointer here, this S1 is out of scope, it will get destroyed. As I said before, sometimes you want to observe if an object still exists. And what you can do is you can call the s.expired method. And this basically gives you true if the object has been deallocated, so it has been removed, or false if it still exists. Sometimes it's a good idea. Okay, do I still have that superhero pointer, or is it already deleted? And what you also can do with weak pointers, you can use the s.lock method, and this will give you the ownership of it. So it basically converts a weak pointer to a shared pointer, which means it increments now the ref counter. And now you have a shared pointer made from a weak pointer. And sometimes if you say, okay, is this still alive? Does it still exist? If yes, then I want to have a shared pointer, because now I want to have the full ownership of this object also here. Okay, then let's have one last quiz for you. Same as always, we have our superhero here, a constructor and a destructor. And then we create here our superhero using smart pointers and call S1 use count. Pay attention what we create and where we store it. Okay, last seconds. Okay. Oh,
yeah. Yeah, it's a tricky one.
Yeah, that's a very, very, very tricky one. What happens here? We create our shared pointer. So, is this the correct one when I go back? Yeah, Batman created, Batman destroyed, and then 0. I think I've never seen 0%. Okay, let's have a look at that. I create a shared object here, a shared pointer. So I create the superhero. This is just Batman, just hidden here. And then I store it in a weak pointer. Weak pointer does not increment the ref count, which means the ref count is 0. As soon as the ref count is 0, the object gets destroyed. So the object gets immediately destroyed. So Batman is created, Batman is destroyed, but I still have this this weak pointer here. So the pointer object still exists. Only the object is destroyed where it points to. So I still can use count, which then returns 0 because no pointer is there. That's a very, very tricky question.
Yes. So since we do not store our share pointer in a share pointer variable, we create it, but then instantly lose this pointer, and then the object gets destroyed because there's no other shared pointer holding this object. Yeah.
So maybe as a rule of thumb, as soon as the first shared pointer should always be stored in a shared pointer, otherwise you will lose the object immediately. Any questions to this or to smart pointer in general? The unique pointer, the shared pointer, and the weak pointer. I know it's in the beginning a lot to write, always this std make shared and so on, but you will see that there are so many benefits, and yeah, it's a very cool feature. If there are no questions, then let's sum it up. Maybe it's the unique pointer, the shared pointer, and the weak pointer again. We talk about different ownerships. So is there just one object, one smart pointer pointing to the object? The unique pointer has a single ownership, shared pointer share it, and the weak pointer has no ownership. Then, as we said, the unique pointer cannot share the ownership. The shared pointer has a ref count, and the weak pointer does not affect the ref count. When should we use it? The unique pointer, maybe if you know that you have only one pointer to this object, maybe in one local function, would make sense. The shared pointer is, let's say the most used one. So I would use that in, let's say, I don't know, 90% of the cases maybe. And the weak pointer, if you maybe want to observe if an object still exists, and then you can convert it to a shared pointer. All right, so smart pointers, as we said, are classes around pointers, and you can use that for primitive data types. You can use it for int, float, whatever, or also your own data types. And as soon as they are not active anymore, they get destroyed immediately, and that's very, very convenient. So you don't have to think about when to delete the heap objects. And
as David already mentioned, although there's a little bit more to write in the code, they come with much benefit and a big advantage. So use it whenever possible.
Yeah. Okay. Then thank you for being here today. And now we have 3 weeks of time for practicing assignment 2 and practicing the smart pointers. And then we will meet in 4 weeks again.
Thank you.
Thank you.